Thank you, Chairman. Very good afternoon to all of you. Firstly, I would like to thank you for staying back for this last session. I was just joking that maybe it's only chairs and the speakers who will be here, but it's good to see more than chairs and speakers. Right. So, this is a sensor packaging session. I don't need to tell you that packaging is extremely important because what user sees at the end of the day is package, right? I mean, we have heard this that everything has to be packaged well, right? Even the stock has to be packaged well, right? So, but I also want to tell you that while packaging is prerequisite, that good packaging, what is also important is what is inside the package, right? So that is also extremely important. And what I want to tell you in the next 25 minutes or so is a journey that we went through in the last decade, wherein we started from research. Which was then translated, this was in Biosensors, translated into a product through a startup, which is now in the market, right? So anuPath is the product, which I'll talk to you, starting from sensors, science, all the way to packaging the complete device, okay? Novel sensing chemistry to lab on farm, sensor system for diabetes and complications. There are several students of mine who have contributed in this work and several funding agencies which have supported us in the last 2 decades. Right? So, you have heard this in multiple talks that, how do we serve the bottom of the pyramid, right? So this was a question that we asked ourselves, right? Can we bridge the healthcare divide, right? And that is when I started my journey in sensor research and in particular biosensors, and started interacting with healthcare practitioners, which is very important because at the end of the day, it has to be deployed, right? We had the fortune of interacting with one of the very well-known biochemists, Dr. Krishnaswamy, with whom the interaction continues till date. And that is when we said, let's focus on diabetes and its complications. So the way you do it, is recruit PhD students. The first generation of PhD student was Shiv Ramakrishna, who completed his PhD in 2012, and he is a faculty at IIT Hyderabad. And then it was followed on with the second generation of PhD student. And by 2015, we were actually sitting on a range of very interesting technologies, right? So that is when this idea of starting a company came in, and we incubated this company. And what followed after that is 2 years of very, very rigorous clinical trials, right? Testing about close to 25,000 clinical samples to validate that what we have done in the lab is really indeed true in the field as well. And 2017 is when we had this fully packaged product coming in the market, right? And as we speak, it has been deployed in multiple places in the country. So the topic is really point of care diagnostics, which is an interdisciplinary task. Biology, chemistry, electronics, of course, manufacturing, and eventually you bring out a product, right? So you start from the scientific discovery and you develop the technology, and eventually if you want to talk about product, you also need to worry about manufacturing. But you also need to think out of the box. You need to build team, and again, this is also a different kind of packaging, right? You need to also think about all these very, very important tasks. If you do all this right, then perhaps you can create one of its kind product. This is the fully packaged product, which is first of its kind in the world. It can do 5 blood tests and 3 urine tests. I will talk a little more about some of these tests as we go on. Just like a glucometer, but we actually go much, much beyond glucometer, right? Okay, so what does it do? It addresses diabetes management and its complication, anemia and malnutrition, kidney disease, early diagnosis of kidney disease, and liver disease as well, right? Completely dry chemistry, no reagents and no steps of sample preparation. Tiny finger prick sample, microliter, of that order, and various other very, very interesting technologies that are supported. And this package strips out here, just like a glucometer strips, you have these strips customized for each one of these tests, right? And with the finger prick, you should be able to measure some of the very, very complex markers such as A1C, glycated albumin, hemoglobin, human serum albumin, ACR, and things like that. Okay, when we started focusing on diabetes, right? Why did we do that, right? Diabetes management is challenge for this century, really, right? If you ask the endocrinologists, they say that diabetes itself is not a disease, it's only a metabolic disorder. But the unfortunate thing is that it affects almost every part of human body, right? Some of the statistics are really staggering, right? It is already said that India is going to be soon diabetes capital of the world, right? So our thought process was that, can we think of a new paradigm in diabetes management? So what is this new paradigm that we are talking about? So I need to digress a little bit before we get into that. I need to tell you something about protein glycation, right? Proteins, as you know, are building blocks of human body or any life form for that matter. Proteins go through a process called glycation. And simply put, protein reacts with glucose and forms what is called a glycoprotein. It's a one-way street. If it gets this converted into glycoprotein, you cannot dissociate it back, right? And that when protein goes through this reaction, it loses its potency. It's not a good thing, right? And what happens is that in diabetics, there is more amount of glycoprotein. And in particular, in the context of hemoglobin, when it reacts with glucose, you form what is called glycohemoglobin. A particular form is called HbA1c, which has become a gold standard in diabetes management and also diabetes diagnosis today. As per American Diabetes Association recommendation, HbA1c must be tested every 3 months, right? Because it gives 3 months average blood sugar in the human body. Okay? Fine. So, what did we want to do at the beginning of this research, right? I mean, glucometers are out there, dime a dozen today, right? But we wanted to bring in what is called time differential glycemic index at point of care. That is, it is very well known that glucose monitoring is not sufficient. It's insufficient for diabetes management. HbA1c has already become a gold standard. So because it gives 3 months average blood sugar in the body, which is extremely important for a doctor to know how diabetic is managing the disease in terms of diet and medicine, right? We said, let's also bring in HbA1c at point of care. And we said, let's not stop there, right? This is a new kid on the block, the glycated albumin, right? In fact, it's not even available in pathology labs, right? The only country which is pioneering this in pathology labs, not point of care, is Japan, right? Where a lot of clinical research has happened in glycated albumin. And this, like hemoglobin, is another protein, but its lifespan is 2 weeks, and hence it gives 2 weeks average blood sugar in the body, right? So that's amazing, right? You have this time differential glycemic indexing if you can do all this at point of care, right? So we said, and also glycated albumin has some very, very interesting implication. It's very important marker in chronic kidney disease and gestational diabetes, right? Wherein HbA1c is too long time to wait for 3 months, right? Because whole pregnancy is just 9 months, right? So we said, let's do all these at point of care. And said, this is a new paradigm in diabetes management, right? And we said, let's not just stop there. Let's build a platform which is so generic that you should be able to add on tests as and when you are able to come up with the newer tests, right? Okay, so what do we do in pathology labs, right? If you look at, just like computing has gone through, based on Moore's law, an amazing transformation, pathology labs have also gone through amazing transformation. Early part of 1900s, people used to do a lot of testing, blood tests, urine tests, and so on and so forth. But pathology lab used to look like chemistry lab. They used to do a lot of titrations of, cook blood and urine in the lab, and they're able to give very accurate information on your disease condition. Fast forward today, pathology labs are very, very sophisticated. You have these autoanalyzers, which are black boxes, and it's like, you sample in and, you get this test results out, and so much so that, oftentimes you don't even know what is happening inside, right? And most of these are based on immunoassays, by the way, right? Which are very good for pathology labs, which are very well controlled ambient. But now we are talking of point of care, where ambient is not under your control. It should operate over a very large temperature, very large humidity range, right? And that is where there's a difference between biosensors and autoanalyzer. If you look at our anuPath definition, very revealing, it says biosensor is a self-contained integrated receptor transducer device, which is capable of providing specific quantitative or semi-quantitative analytical information. More importantly, a biosensor should be clearly distinguished. from a bioanalytical system such as HPLC, which requires additional processing. If you look at what has happened in the past, this is a receptor transducer biosensor device. Sample comes in, which is a biofluid, and you get a signal out. Of course, it has to be accurate and efficient, but what is more important is this receptor, right? Which really is a core of this, biosensor, right? What has been done historically is that enzymes and antibodies are used, which are extremely good for immunoassays in the pathology labs, but not so good because these are biomolecules after all. They are finicky and they're not going to be robust over huge range of temperature and humidity variation, right? We said, let's stay away from enzymes and antibodies. That was a very conscious decision and that was a boundary condition for us. So we said, let's only look at specific ligands and metal ions, chemical receptors. In terms of transduction, we said, let's look at electrochemical pathways. Right? So this is how we started this whole thing, right? And in the context of electrochemical sensing, I don't need to tell you that almost more than 80% of glucometers today are based on electrochemical sensing technology. So Salil and Clark, we can call him a father of biosensors, right? Who actually came up with this innovative idea of glucose oxidase-based, electrodes. The key in glucometers really is this test strip, right? To really dissect these test strips, what is out there is really, carbon screen printed electrodes, counter working and reference electrode. And this is your equivalent circuit of your, glucometer strip. The most important thing here is a working electrode where all your action happens, right? You need to functionalize this working electrode with the appropriate receptor, right? That is the key, right? In glucose sensing, the receptor is glucose oxidase enzyme, right? And that gives a specificity to the sensor, right? So what you really do is that you apply certain potential, which is called the redox potential, and you measure the oxidation reduction current, which is essentially due to the chemical redox reaction that happens at the working electrode, right? So in the context of glucose sensor, you have glucose oxidase enzyme, you have mediators invariably such as ferricyanide, you have glucose convert oxidized into gluconic acid, there's electron transfer process, and then through the mediator you essentially measure the electron transfer at the working electrode, and your electron current that you get is directly proportional to the amount of glucose that you have. You generate the calibration curve, you have a glucometer, right? Fine. Look at the trends that has happened, right? There has been an exponential growth in literature in terms of biosensor research, right? Since the advent of glucometer. But you ask the question, what is out there in the market, right? And the hard reality is that majority are glucose sensors, right? At the point of care, right? So the question is, why don't we have other sensors at point of care, right? And there are a lot of very, very critical analysis that is done. I'll just give you one example, the review article, and sort of it all point out to this very important thing, and that is, at this point, the bottleneck of biosensor is the lack of fundamental understanding of biorecognition macromolecule. That is the key. The receptor is the key, right? Staying away from enzymes and antibodies, right? That is very, very important. Right? Fine. So we said, let's start looking at it, right? And this is how the journey began, and I'll just give you one or maybe two examples in the context of albumin and glycated albumin sensor, right? Now, we wanted to do glycated albumin because this was an innovative paradigm for diabetes management, time differential glycemic indexing. But first you need to detect albumin, right? Only then you can talk about a fraction of albumin which is glycated, right? So look at albumin, it's a protein made of amino acids, 585 amino acid, but there's a very important difference compared to hemoglobin. Hemoglobin is a metalloprotein, right? There's a redox active iron in hemoglobin, but in albumin there is no redox active element. So in the context of electrochemistry, albumin is like an insulator. There is no way you can extract current out of albumin, right? So then the question is, how do you really build an electrochemical albumin sensor, right? And that is why you do not have any electrochemical point of care albumin sensor out there, right? Okay, and that is how you start worrying about these problems, right? And we call all our sensors that we have are physiology inspired sensors, right? We have sort of learned from what happens in human body. We started asking the question, okay, we understand albumin is an insulator, but can we do something? Can we learn from physiology and do something, right? So what does albumin do? I said already that albumin is a protein which has a 2 weeks lifespan in the human body. It is actually born in liver, it's released into bloodstream, and it stays in bloodstream for 2 weeks. The question is, what does it do for 2 weeks? Right? It turns out albumin is actually called a molecular taxi in the human body. Right? Albumin binds to a whole range of substances in the human body. Fatty acid, metal ions, bilirubin, including pharmaceutical drugs. You take, paracetamol or Tylenol, it binds to albumin, transported to rest of your body, and that is how important albumin is, right? So then we started thinking about a technique. Can we use this binding property of albumin and develop an albumin sensor? And we sort of discovered that copper has one of the highest binding affinity to albumin. In fact, it's 10 to the 16 per mole. That is the association binding constant for copper, right? And copper is redox active, remember that. Copper has multiple redox oxidation, right? So the idea that we had, hypothesis was that, okay, let's build a point of care albumin. Albumin binds to copper, it's very well known. Copper is redox active. So let's create a strip, just like a glucometer strip, except that I do not have a glucose oxidase here. I have copper salt, some copper salt, right? The devil is in the detail, right? How do you really do that copper salt functionalization? What should be the pH and so on and so forth? But if you can do that, right? Hopefully, if you have a electrode, which is what is required to do electrochemistry, you have a membrane on top of it, which is functionalized with copper salt. You put the drop of the blood. Albumin should bind to copper. Albumin is very heavy molecule, 65 kilodalton. Copper is extremely light. So if albumin binds to copper, that copper which is bound to albumin is lost for your electrochemistry, right? Only the unbound copper can contribute to your electrochemistry current, redox current, right? So the hypothesis was that you should see a current which should be an inverse function of albumin concentration if everything goes well, right? And this is how we sort of started, building the albumin sensor. You do a lot of experiments to figure out what should be the right concentration of copper salt that you need to put in, And initially we started our experiments with not blood sample, but with simple buffer, dissolving a pure albumin, which is procured from Sigma Aldrich, dissolving it in sodium chloride buffer, validating the hypothesis in the first place, then moving on to plasma, which is benign compared to a whole blood, right? So make sure that it also works in plasma, and then go on to the whole blood, right? And eventually, as I said, this whole journey was, multiple samples, thousands of samples were tested, and eventually we were indeed able to show that, you can have a completely dry chemistry and really build a very good albumin sensor, right? Which is point of care. Okay, if you have albumin sensor, maybe you can also think about glycated albumin. Right? So what we did was that we used a very standard assay, which is there in pathology labs, which is essentially called a boronic affinity principle. Boronic acids, right? The phenyl boronic and aminophenyl boronic acids have a very high affinity to glucose moiety, right? So if you have proteins partly glycated proteins can bind to boronic acid, right? And this is a very, very standard assay that is used in pathology lab. So our idea was that let's think about building two electrochemical cells on a single strip, right? Glucometer strip and albumin strip I talked about is a single electrochemical cell. Now I'm talking about two electrochemical cells, right? So, one of them should measure the total albumin and the other one should measure the non-glycated albumin. Trapping glycated albumin, right? So if you can do that, then you should be able to measure the glycated albumin, which is essentially expressed as a fraction of total albumin, right? On a single strip, you're able to, get the glycated albumin, right? So this is how we sort of, the problem was that glycated albumin is not even measured in pathology lab, right? So we resorted to mass spectroscopy. This is the gold standard, right? Using mass spectroscopy, you can figure out whether your protein is complex with a glucose moiety, right? And a very small mass change can be, figured out. And in addition, as I said, in Japan, there is this assay that is available, and we actually got that assay, set up the whole automated assay on a Roche analyzer. And we have we sort of tested our point of care glycated albumin assay against the, what is called the diazyme glycogap assay, which is, which can be set up on a Roche autoanalyzer, right? And again, we were able to sort of validate our technique and made sure that, the whole thing works very well, right? So that was in terms of the actual sensor, which is a disposable electrochemical strip. But we're talking of complete system, right? You need to build a whole package, right? So now you need to actually build a potentiostat circuit, right? Not just a single potentiostat, multi-potentiostat circuit, right? And that is what we started working on. And again, there were very, very interesting challenges that we had to sort of overcome, because this is handheld device, right? It should really work at ultra low power, right? And we'll explore multiple design options, multiple system design options, right? And should it be as simple as a benign glucometer, or should it be as complex as your handheld cell phone, right? And eventually we decided neither one, and it should be somewhere in between, right? So, we came up with an optimum system architecture, and we sort of developed this whole system architecture. And when you're talking of completely packaged device in the context of medical device, it should also qualify certain standards, right? Radiation standards. One of them is emitted radiation standard. So we also had to worry about that. Our first prototype actually failed this emitted emission standard. But then we had to improvise this further. Very interesting improvisation had to be done, keeping in mind the form factor of fully packaged device. For instance, making sure that you take care of the ground bonds, you separate your digital and analog ground. You also put the metal cans, sort of build a Faraday cage in your PCB, right? So with all that, we were able to, qualify the emitted emission standard with a huge margin, right? And even the device enclosure, the whole package, eventual package, right? It went through multiple iterations, right? How should it look like? The look and feel of this for the end user, right? Including the color, what should it be color? I mean, that is very, very important for a fully packaged device, right? It went through multiple evolution, and what should be the material, right? And we have to come up with the right blend of ABS and polycarbonate, right? So that it is resistance in fall, because when you're using it in the field, you might actually drop it, and it should survive all the chalk, right? So this was very, very interesting. Okay, you have this completely packaged device. It has to be eventually put it in a carton, right? That is also part of your packaging, right? How should that be, right? So again, we went through multiple designs, right? Because now we are talking of a complete product. It should actually go to the user, right? You need to figure out the aesthetics, get a user feedback, right? Just being in ivory tower and just saying that I want to publish and not worry about it will not take you too far, right? So we actually went through all that, and we arrived at the right user-friendly package, which will really be acceptable for the end user, right? And now what? It has gone through all this. It has got multiple recognitions, right? And including the MIT TR35 award, right? And what is more important is the recognition from the field, right? It is being used as we speak in multiple locations. One of the biggest is the National Rural Telemedicine Program by the Tata Trust, right? And they have actually deployed it in several resource challenged villages, where you don't have any facilities, but this device is being used, which is able to sort of really transform the way the healthcare is provided, right? And at this time we are actually doing another version for home diagnostics, right? And this would not have been possible but for an amazing team of people that we have. Okay, that's it. Thank you very much.